Year 11, here are the answers to your 5-day. Let me know if you have any questions about those. So today we're going to be looking at applications of antidifferentiation to kinematics. And so given the acceleration, we're going to look at how we can find functions for the position and velocity of particles. Previously, we saw that if we have a function for the displacement of a particle, we can differentiate it to give the velocity, which is the rate of change of displacement with respect to time, and we can differentiate the velocity to get the acceleration, which is the rate of change of velocity with respect to time. We can go in the other direction. So if we have the acceleration, we can anti-differentiate it to give the velocity. If we have the velocity, we can anti-differentiate it to get displacement. So here is the example we're going to work through. I'll give you a moment to read it. So we're going to find expressions for the velocity and displacement to begin with, before we even start thinking about these questions. Now, what we often do is decide that when we're working vertically, upwards is positive. This isn't always the case. We can actually choose either way round. We're going to do upwards being positive this time round. So our acceleration, because it's due to gravity, which works downwards, is -10 meters per second squared. We can anti-differentiate that to find the velocity. Now, we need to remember the constant of integration when we anti-differentiate. We find this constant of integration by finding the velocity when t equals 0. We're told that the initial velocity is 15 meters per second, so we substitute t equals 0, v equals 15 in to get c equals 15. So our formula for our velocity is -10t plus 15. We can do the same thing for the displacement. We anti-differentiate the velocity. Remember that there is going to be a constant here. I've called this d for displacement, but also to differentiate it from the c that I've already used up here. Because the building is 20 meters high, and we're taking the floor, the ground, to be d equals 0, when t equals 0, my displacement is 20, and so d is equal to 20. And so that's my formula for my displacement. Now I have these 3 relationships, I can start broaching the questions. The time taken for the stone to reach its maximum height. When the stone reaches its maximum height, momentarily its velocity will be equal to 0. So I can solve the v equation when it's equal to 0 to find what time that is. It's at 1.5 seconds, and so that's the time taken by the stone to reach its maximum height. To find the maximum height reached by the stone, I need to use my displacement function. T is equal to 1.5 when the stone's at its maximum height, so I just substitute that in and evaluate. The time taken for the stone to reach the ground. When the stone reaches the ground, S is equal to 0. So I set my S equation to be equal to 0 and I solve for t. You see I get 2 solutions to this quadratic. I reject t equals -1 because we're only thinking about things with positive time. When the stone hits the ground, so we know this happens at t equals 4, so we substitute that into our velocity equation. We get -25 meters per second. -25 means it's heading down at a speed of 25 meters per second. So that's the speed that it's travelling at. It's always best to interpret these negatives in terms of how the question describes it. So, using that example, you can now answer questions 1 to 6 from exercise 22B. Make sure you mark your work as you go. And let me know if you have any questions. Thank you.